All right, so we wanted to make sure to end in a high note. So Percy Diakonis has given one of the previous Birnbaum lectures in this series, and we're delighted he's back with us to tell us about an analysis of spatial mixing.
Thank you, Yuval, and thanks to everybody for being here on this freezing time. I'm cold. I don't know about you. So this is a talk which is a report of joint work with Soumik Pal, who you don't need to see a picture of him. You can just look at him. He's right there. And I want to tell you 4 things during this talk. And so if I list them, there's a hope that I touch them all. One is a set of problems, which are the spatial mixing problems. And I wouldn't be at all surprised that somebody says, oh, there's a literature on that in this or that part of the world. I haven't been able to find it yet, so I'll be happy to hear more about it. There are a lot of natural problems, and I'll talk about that. The second thing we have is a set of models which, even if they're not infinitely realistic, they are somewhat realistic, and they allow analysis, and so we have some theorems. The third thing I want to tell you about it, there's a new proof technique which is the method of shadow permutations. And it seems to have some legs and be good for proving things in other types of problems. I'll try to describe that. And the fourth topic is there's an interesting diffusion limit, which has nice, it's a generalization of reflecting, higher dimensional reflecting Brownian motions that has some nice properties, and maybe somebody will be interested in that because you like diffusions, even if you don't like real problems. Oh, sorry. Okay. And so spatial mixing, let me start there. So I don't know about you, but I cook, and when I at home and when I'm mixing a pan of onions and potatoes and things with a spatula, somehow they roughly get evenly browned. And I've often thought, is there some ill-posed ergodic theorem which could allow me to study the browning? And I have written a paper about the mathematics of cooking potatoes, and it's an interesting subject. There's a large engineering literature on spatial mixing, and people, for example, manufacturers who make cake mix, there's flour and coloring and sugar and salt, and they go into a big vat, and then there's a mechanical arm that does this for a while, and the stuff gets all mixed up, and you want to know how long should I mix it. There's a phenomena that they talk about which is called overmixing. You don't want to overmix for 2 reasons. One is it takes time and costs money, and the second is stuff breaks if you mix it. Chemicals change. That you don't want to overmix. And so pharmaceutical manufacturing is similar, and there really is a lot of mixing literature. I put some of it on the handout. If you want to look, and there's huge compendia of engineering studies about spatial mixing, and it's mostly it's non-stochastic, and so there's stuff for us to do if you like doing that. Now, the kind of spatial mixing I'm going to talk about in this talk is what I call smushing. So, there are 3 ways that people shuffle cards. There's riffle shuffling, overhand shuffle. You can't see, but put the cards on the table and you do this. So I'm doing this with my hands on the table. Okay, so you can all try it. So that method of mixing is not just for kids. In California, poker's legal, and in California poker clubs, all of them, that's the way they mix the cards. Okay, if you watch ESPN poker tournaments, that's the way they mix the cards. In Monte Carlo, that's the way they mix the cards for baccarat. So it's a real method of mixing, and then if you're me, it's natural to ask, well, how long should you do this for? And if you're me, or you maybe, you might ask, well, if the cards aren't well mixed, why aren't they well mixed? How can I take advantage of it? Or how could somebody take advantage of me? Or however you want to phrase it. Okay, so that is an example of spatial mixing that I'm going to introduce some models for. But before doing that, let me just report what's the answer. That's usually also of some interest. So how do I know that? Well, I had some students, and we took a deck of 52 cards on a big table, and we mixed them for t seconds. T was a minute, 30 seconds, 15 seconds. We mixed them for t seconds, gathered them up, of course, and so that, gathered them up so that they're a deck again, and then read them off one at a time, so we knew the permutation, and repeat that, capital N times. So I have some permutations. Now, if you say to certain computer science scientists that I know, I want to test if the cards are well mixed, there's 52 factorial different arrangements. That's around 8 times 10 to the 68th, and I have 200 observations. Well, you can't do that problem, right? I mean, how could you possibly answer that question? For sure, all the permutations that you get are going to be different, and so you've got 200 balls dropped into 10 to the 68th boxes, and you want to test for uniformity. On the other hand, if mostly the ace of spades is near the top, you'd be stupid if you missed that, right? So let's think about it together. You don't only have to do math, you're allowed to think also. So consider spatial mixing the way I just was doing it. The cards start out in order, 1 up to n, and I'm doing this. If you don't do this long enough, why wouldn't the cards be random? Think I. Okay. I thought there'd be, you're just sliding them around. There'd be too many cards which were originally together that are still together. Right? You're not riffling them. They're kind of, that's a guess. So that's a statistic. I'll call it, I won't have to write it down. If you have a permutation sigma, T of sigma is the number of i's such that sigma of I plus 1 is equal to sigma of I plus 1. Cards which were originally together that are still together. So that was one test statistic. And we look at the position of the original top card, the position of the original bottom card, take various metrics on the permutation group, and look at how close you are to the original starting order. So we had about 10 statistics, and we just did ad hoc testing. I know if the cards are well mixed. If you look at the number of adjacencies, that should be Poisson 1 to good approximation. And so you could compare the data to the distribution and just see if it makes sense. And on the handout, let me first tell you, for mixing for smushing, I call it smushing, for a minute, it passed all the tests. Of course, that's not a proof of anything. On the other hand, probably okay. No, it wouldn't shock me if somebody said, "Oh, I'll try this test." No, well, I forgot that, right? But still, it is why we prove theorems. After 30 seconds, it wasn't good. It wasn't bad, and I put the data on the handout so that after 30 seconds, how many times we don't, not to be confusing, there were 52 cards in the deck, and then we shuffle them 52 times. I mean, I had 52 repetitions, so there's 2 52s. Hope that doesn't confuse you. And there's how many, so the number of adjacencies could be 0, 1, up to, 51, but it was mostly 0 up to 5, and how many times was it 0, how many times was it 1, etc. And so I give you those numbers, and then if you do any kind of test, a chi-squared test, or I've done various other kinds of tests, the data follows the theory. That is, it does seem as if a Poisson one model fits that certainly well enough. And just in contrast, so after 30 seconds, more or less all the tests were passed, and given that we did a lot of tests, seems to be okay. And after 15 seconds, it failed all the tests. Okay, that you can see. For I gave the data after 15 seconds, and the mean number of adjacencies is 1, and the average in my data was 7.5, or something like that. So it just the data doesn't fit the model. Okay, so the answer is about 30 seconds. Okay, now we're going to do a lot of math, and okay, but the answer is about 30 seconds. So that's my contribution to reality. Okay, so let me talk about some models, and these are models for spatial mixing. And so I'm going to model a table. I'll call it D, and often it's going to be the unit square, but the table you could change everything, and so that's my space that I'm mixing on. And now I'm going to do what I just did, namely I'm going to have a deck of cards. I'm going to spread it out, and maybe it's on a line, and the cards are like this, and they're labeled x1, x2, up to xn, okay, and xn. So that's my initial ordering of the cards, and I'm going to treat the cards as point particles. I'll change that in a minute, but just bear with me. Think of those as the centers of the cards. Now there's a hand which I'm going to take to be a disk U, which is the set of all points in the plane such that z is less than or equal to delta. So there's a hand, and again, you could make it a more real hand, but the math will work just fine, but suppose it's a disk. And now the dynamics are the following. I'm going to make this much more careful, but let's first speak English to each other. So the hand goes down, and then it's going to rotate by an angle theta, okay? All dots under the hand will rotate rigidly with the hand. Okay, so, and then the hand's going to hop, and it's going to rotate by theta prime. And then the hand's going to hop, and it's going to rotate again. And the thetas are going to, say, be from some distribution on angles. And now what'll happen if you do that, the dots go all over the place, right? You can just picture that, right? They actually do go all over the place, and we'll talk about that in a second. And so the dots are labeled dots; they go around, and then at the end, after however much time t I do, I project them back onto. You could project them back onto the original line or onto the x-axis, and then gather them up left to right. Okay, so that's a model. It's not a realistic model, but it's a model that has some true spatial aspect to it. Okay, and you can ask, how long does it take? Do the cards get random, and so forth.
How are they hopping?
I'll say, but right now I haven't specified. But that would be another parameter. For example, I could just make them hop uniformly. I will specify in a second, but I'm just trying to get the idea across first, because I'm going to actually change the model so I can prove something. Okay, so that is some kind of a toy model for spatial mixing. And so I now want to say more carefully a model. One of the things, if you watch movies of fluids mixing, is you have to pay attention to the boundary. That is, stuff near the boundary mixes much slower than stuff inside, and we're going to pay attention to that. So here comes a more careful description of a model, and we call this the gather and spread model. Gather and spread. Before I do that, I should have said the following. Let me finish this reality part. The way I described it, the cards are points, right? You could take the points to be the centers of actual cards, and then you have to say something about what happens to the cards when they interact. And we make a dynamics. We made a dynamics in which if cards come together, they go above or below each other with probability a half each. And it's actually three-dimensional, and you have to kludge around, but it's not so bad to do. And I have had several students who wrote code to do that. And so that model with real cards, well, that's a math model, but that model we can run on a computer. Okay, and that's we have run it on a computer. And there are some people put friction in, and so you could, so you could run it and try to study it on a computer. I mean and we have done that. I have a student who went to Google, and am I allowed to say that here? And Mark Coram, and he said, well, I don't know about these models, and he made machine-readable cards and with a movie camera, and they were translucent cards, so you could see through. And I have movies of cards doing this where I know where all the cards are. So you could, it's a little subject. Okay, so here comes the gather and spread model. So there's gathering and spreading, and so first there's gather. So here's gather. The hand, this disk goes down at a point, and so for Z and Z naught in D, in this unit disk at the moment, introduce a function G, gather up at Z naught, of Z is going to be Z naught times delta of if Z is contained in Z naught plus U plus Z times delta of Z is not contained in Z naught plus U. So the disk goes down, the disk goes down centered at Z naught, and all the points under it are gathered together to the point Z naught. That's what this formula does. Okay, you just gather the points together. Is that okay? No? You? Did I lose you? Do you know, no, is this description of gathering cards okay, or have I lost you?
No, I haven't lost.
You're not lost, or you are lost?
I'm not.
You're not lost. Okay, I think okay. So that's this gathering step. Now, because the cards will now be all together, and when they go together, we're assuming they go together at random. Because the cards are all going to be together, they might tend to stay together, and so we're going to have to do something about that. And also I want to attend to the boundary. So if I'll let x tilde be well, 0 if x is less than 0, x if 0 is less than x is less than 1, and 1 if x is bigger than or equal to 1. And so that's just a function which is like this, that truncation. And if z is a pair of coordinates x, y, we'll let z tilde be equal to x tilde y tilde. That just keeps us in the unit square, okay? And now I'm going to extend where the hand goes. So let d bar be equal to d, the sum of d and u. So I'm going to fatten this out by delta. It's just a slightly bigger set. And now, if for z naught contained in d bar minus d, I'm going to allow my hand to go slightly outside. Let g z naught of z be equal to z naught tilde. So if I try to gather to outside, I go to the boundary times delta, same thing, plus z times delta not contained in. So there's a picture on the handout. If I'm paying attention to the boundary now, and I'm allowing my hand to go slightly outside, and then I will stick on the boundary. Okay, so that's my gathering operation. And now there's a spreading operation. I'm trying to, rigorously define a stochastic process, and so, okay. And the spreading operation, let me just write it down. It has some parameters in it, but I'll explain that. So the spreading operation is, again, it's a function f of, say, w and theta sub s of z. Okay, we'll explain this. What's it equal to? So it's, if z is my coordinate, this is equal to x 1 tilde y 1 tilde, x1 tilde y1 tilde, where x1 is equal to x plus x cosine theta, and y1 is equal to y plus s sine theta. And so, and this tilde is the same tilde. So what this does is it takes, what's w? That's a good question. This is if and it's equal to z otherwise. This is if z is contained in w plus u, and it's otherwise. So you put the hand, the hand is down at some point, and it pushes the points at angle theta, just rigidly pushes them. That's what this is doing, except if they hit the boundary, it sticks there. So there's 3 parameters. This is where the center of the pushing is. This is the angle. The theta's in 0 to 2 pi. And s is how much you're pushing. So, x plus s cosine theta. So that's just pushing. Okay, so that's spreading. And I don't allow myself to go outside of the table. Now I can define a process, okay, which I'm going to call z of t, and that's z1 of t up to zm of t. I've got m cards, and this is the position in the unit square of each of the cards. So zj is contained in D, and it starts someplace. Z at time 0 is equal to some z naught, vector. It starts someplace in the unit square. And then you run a rate lambda Poisson point process, just a vanilla flavored one at the moment. So I'm going to be putting my hands down at random uniformly in the disk, and this will have times t1 less than t2 less than t3 when it jumps, and then you define z at ti to be equal to, well, what? Sorry, this is a vector, and I'll put a J in there, the jth card, is epsilon ij, I have to explain that, I will, of z of, sorry, I have to gather and spread. So, sorry, first let me gather. G at Z, G at W I of Z of Z of T I minus 1 plus 1 minus epsilon ij. This will all be clear in a second, times Z at Zj at Ti minus 1. And then I'm gonna spread these, and then Z of T ij is equal to f at f of, I should look and get my notation right, at z of, sorry, I've got my notation funny. I'm gathering to wi, but that's okay. Z naught of Ti minus 1 of theta I and S.
Well, describing words,
yes, what I'm doing. Yes, I will. Thank you. So at the times of a rate lambda Poisson process, I'm going to gather, except that these are coin tosses, and here epsilon ij or id with 0, 1 with probability p, and so I'm going to gather the cards, and then at this point, and then I'm going to take some of the cards which are gathered with probability p and move them rigidly, and then I'm going to leave the other ones where they were.
And you have these parameters of how much to move them.
Yes, so there are many parameters here. There are, so the where this is centered are going to be, we'll make random walk models in a second, but at the moment where the center of the gathering is, S is fixed, Wi or ID in D bar, so I'm going to pick where to put the hand, that's Wi, and I'm going to gather to that point. And then I'm going to take some of the cards at that point with probability p. P might be a half or something like that, or whatever it is. And then I'm going to slide them in theta I or IID from some measure nu on 0 to 2 pi. So don't give up trying to understand, and I won't give up trying to explain.
Clearest when you explain it in words. So each of the cards is moved in its own angle, or there is a batch moved together?
The batch moved together. So I gather the cards, I put my hand down at random, I gather all of the cards under my hand, I suppose I have 5 of them, I flip a coin for each of the 5 cards, say 3 of them come up heads, and I move those in a random angle for distance s. That's my model. Good. Yeah, words are better than anything.
But Percy, it seems to me that earlier you said that you would actually...
I'm not doing that right now. I will come back to it. I'm not rotating.
Just shift.
Just shifting, right.
Just
shifting. Right. And just to say, we actually can try it. If you look at the handout, there's a picture, a nice picture by one of Soumik's students, which we had 250 cards, okay? They all started out at the center of the square. It's a 5 by 5 square. And then this algorithm, and delta, I believe that delta is 1 and S is 1 and P is a half. Those are my parameters. And we ran the algorithm, they ran the algorithm 600 steps, okay? 600 steps. And you can see the cards. Well, some cards get all over the place. Now, if you look, that's not 250 dots, right? It's about, 60, 70 dots, something like that. So those dots all represent little packets of cards, because there are little packets of cards. And there's math problems that come up. How many cards are there in each packet? You'll notice that there are cards on the boundary. That's part of the rules, and so, okay. So you could do that, and then you could project the cards back down onto the x-axis, and then gather them up left to right. So you might wonder, what do I do about ties? Well, let me say two things about that. If the initial position of the cards has all distinct positions, as in my picture, when I gather, since a packet of cards is gathered at random, and if I slide two packets together, I do this Gilbert-Shannon-Reeds model. If the initial cards start out at all separate positions, when I gather and spread, every packet of cards is in random relative order and independent of all of the other orderings. And so I can, at the end, just project the packets down to the x-axis and pick them up left to right. And that's fine. I mean, that's... If not, if I'm worried about that, I have to think that, when I pick up a packet, it's randomized. There are many variations of this model. I've tried to say a specific one. In between the jump times of the Poisson process, it stays fixed. So that, okay. So sorry, it's a lot of words, but it is a mathematical model that you can now run on a computer and study mathematically. And just to say we got someplace, here's a first theorem, okay? So theorem 1 is, let gamma of t be the induced permutation. That is, this is a process on labeled particles in a square, and then I have a mechanism, namely project down onto the x-axis and pick up the packets left to right, that gets me a permutation, and they started out in order 1 up to n, and 1 up to m. So let gamma of t be the induced permutation. There exists a c, which I'll be explicit about in a second. It depends on all these parameters. It's c of, p lambda, what else? The measure nu that I'm my angle, and something s, right? But anyway, it's some function, such that the total variation distance of the law of the permutation after time t minus the uniform, and this is total variation on the symmetric group Sm, is less than or equal to e to the minus c times t over m. So, period. So what that says is that, depending, of course, on what c is, if t is, 10 times m, or whatever it has to be, this is small. So this says roughly that m steps suffice.
What was M?
M is the deck size. So the permutation in Sm. Okay, so I have m cards and m steps suffice. And in a second, well, in 5 minutes or some time, we're going to take a diffusion limit, which I'll explain, in which the Poisson process moves faster, but the amount it moves, the amount of shifts you do, S S is going to be 1 over root lambda, and lambda is going to go to infinity, and there'll be a diffusion limit. And so theorem 2, in a diffusion limit, which I have to explain, there is a diffusion limit. And I certainly don't remember this formula, but I did write it down. If t is m over capital theta, which I'll explain, plus another constant times square root of m, then, and sorry. Okay, sorry, I got this goes over here. Okay, so here we wrote down what C is, where theta is equal to delta squared over 2 p pi squared sigma squared, 1 plus 2 delta squared, times there's another Bessel function, k0 of squared. You can't look at this, but we did the work. Sigma delta square root of pi p1 minus p. So in a diffusion limit, we can say what C is. That is this mixing time. For beyond this time, the total variation distance is less than a quarter. I mean that's a mixing time, and C prime we can say some things about too if we had to. But so we can say some things. Okay, so we're at the end of part 2 of this talk, namely, I just said a model, and more models are coming. Or I said some models, and more models are coming. And I gave an example. I mean, I try to be a little bit careful about the modeling, or at least state a theorem. And now this is not sharp. We don't really have a good guess, but we think the answer might be log m, the real mixing time. So we don't have a good guess.
So can you remind us what is the size of the hand? So
the size of the hand is delta.
Okay.
And so delta is fixed here. I have to say what the diffusion limit is, but sigma squared. So my assumptions on the direction, the choice of our assumptions are nu of cosine theta equals nu of sine theta is equal to 0. So we're unbiased in the direction we're moving. And this is also equal to the correlation, cosine theta, sine theta. I didn't say that. And sigma squared is equal to the expected value of cosine squared theta. So that's how variable the angle is. And P is the coin toss probability. And so no, that all. I just. If we thought we had the right answer, I would pay more attention to this. There was a lot of work to prove it, but anyway. Okay, so one thing I'm hoping for, I think that we're both hoping for, is that you'll get annoyed, given that I've been so specific about the modeling, and given that the modeling is pretty far from real random shuffling, and that somebody will get annoyed and make a better model, and that's just fine with me. I mean, go right at it. These are the absolute first theorems that I know about spatial mixing. Okay, so the next thing I want to talk about is the argument that the proof technique, I think, is quite interesting, and as you'll see, it applies to all kinds of other things. So that's this method of shadow permutations. So here comes, well, I hope the red will work. Yes. Shadow permutations. And so just to say something, let me say a discrete spatial mixing model, which I like thinking about. I find it's useful. But as you'll see when I get there, the argument that I'm going to give for these kinds of theorems works for the model I described and for lots of other models. So suppose I have a graph, say the vertices of a square or something, any graph, a finite connected simple graph. And I start out with cards on the vertices. Okay, so that's a possible way of starting. And here's a different mathematical model, but similar. Each time, you can do it in discrete time or continuous time. Instead of putting the hand down at random, pick an occupied site at random. Uniformly, say. And then put your hand down, and then pick one of its neighbors. At random, and you're not allowed to go outside of off the graph. Pick a neighbor at random and cut off a binomial number of cards. Binomial number. So I'm on a packet. It could just be one card with parameter p. So cut off a binomial number of cards and move those to the adjacent pile, and when two piles go together, they shuffle together in the way that cards riffle shuffle. Cut off a binomial number and move to an adjacent, move to the adjacent site. So that's, similar, but it's now on a lattice, so I find it slightly easier to think about. And then at the end, pick up the packets in a prescribed order, top to bottom and left to right or something. At the end, pick up the packets at any time in a prescribed order. Okay, so that is that's a similar model, but just I'm in discrete space, and again I'll let gamma of t as I said there, and then the hand. So the hand can do nearest neighbor random walk, or that won't matter, but okay. So at each time, let gamma of t be the induced law, the induced permutation. On SM. Okay, and now I need something else, so if this is, I'm trying to prove something, let pi be uniform in SM, just a randomly chosen permutation. So it's certainly the case that sigma composed with pi is uniform. Sigma composed with gamma of t. Sorry. Sigma of t, which is equal to pi following gamma of t, is uniform. That is, if I have any permutation and I relabel the cards by a uniform random permutation, I have a random permutation that's left. That's clear, I hope. And now I'm going to introduce a process on permutations, pi star of t, the shadow process. Here's how it goes. Or pi star of 0 is pi, so it's uniform. And at stopping times, which I'm going to, so let f of t be the number of fixed points in pi of t. Okay, so permutation, maybe it's empty. And when all the points are fixed, you stop. So just to say that now, stop when f of t is m. When we're at the identity. And at a given time tau, which is going to be a stopping time, but at time tau, there'll be some stopping times. No, I don't do that. I don't do that. So I've got this pi. Suppose that pi star at t has, suppose that I naught is the smallest non-fixed point. Okay, the smallest point that's not fixed. So here's I naught, and it gets mapped by pi star to some j naught. And since j naught is bigger than I naught, here it is, and it gets mapped to some k. That is, j naught is different from I naught. It's not a fixed point, and j naught can't be a fixed point either. It has to get mapped to it has to get mapped to some other point k. Now, I've got my dynamics. Let tau be the first time bigger than t, that the x of j naught of t, that's the positions of the cards, is equal, at tau, is equal to x sub I naught of tau. So I'm running the process. Look at the first time that cards labeled j naught and I naught are at the same place. Okay, that'll happen eventually in these kinds of dynamics. Then set pi star at time tau to be equal at j naught to be equal to j naught, and pi star at time tau of I naught to be what it has to be, namely k, and the rest alone, rest as before. So when the two cards come to a common site, in the shadow permutation, you fix j naught and then adjust pi star the way it has to be adjusted. And notice that each time you're increasing the number of fixed points by at least one and maybe two, if there's a transposition there. And then compute the new number of fixed points, f of tau, and keep going. That is, keep running the process. That is, there's now a smallest non-fixed point in here, otherwise you stop, and then wait until those cards come together, etc. Okay, so this is a process on permutations, which we call shadow permutation process. And claim, two claims, and you stop at call it tau star where f of tau star is the identity. So that, of course, could be at time 0 if your shadow permutation happens to start at the identity, then you stop at the identity. Lemma, proposition. For every t, 0 less than t less than infinity, sigma star, which is pi star of t composed with gamma of t. So I've got my permutation. I'm shuffling the cards. At each time t, there's an induced permutation. Suppose I relabel the values of the cards by this pi star is uniform. So the switching of the packets, what it does is it follows the dynamics well enough so that this is, of course, this depends on t. So this is uniformly distributed on SM. And a corollary of that, and of course, 2, of course, at time tau star, pi star at time tau star is the identity, right? Because the pi star is the identity permutation, and so sigma star is gamma of t. So this gives you a coupling. Right, this argument gives you a coupling, namely, you have the process that you're studying, gamma t, and then you have a uniform distribution on the same probability space, and so corollary of this is the total variation distance between the law of gamma of t and uniform. Is less than or equal to the probability that tau star is bigger than t. So, and that's for very general dynamics. That is, here I could move my hand any way I like. It could go, my hand, the way I'm moving cards could be some kind of simple random walk, or it could be picking a packet at random, and that doesn't matter. And this same argument applies in the continuous setting. As soon as the cards come together, they're exchangeable, and then this argument works. And so now you still have the problem of you have to bound this tail. But that's more a standard probability problem, and in the settings that I told you about, we can give bounds on the tail of this. But this argument, works for this class of cases. Let's see. So I want to at least say this beautiful process that Soumik constructed, which is the diffusion limit, in the hope that somebody else might find it as interesting as we do. So let me cut to I know that time is essentially getting close to over, so. Okay. So time is over. Well, then maybe I will. If somebody wants to ask about the diffusion limit, I'll be happy to tell you about it. Okay. I'll consider it asked. And going back to the continuum. So this is the fourth part of my talk. Thank you, Yuval. Thank you to all of you for still being smiling. We're going to let, back to the continuum, let lambda go to infinity, take s, the amount I move, to be 1 over square root of lambda, and suppress the gathering except, well, let me put it this way, gathering allowed with probability 1 over lambda. So I'm doing this process that I started with originally, and I'm putting my hand down at random, but instead of gathering, I'm just going to move the points direction in the chosen direction for distance 1 over square root of lambda, and but with probability 1 over lambda, I'm going to do the gathering step. So it's a process with less gathering, but points moving all around. Then this process converges in Skorohard space to a reflecting jump diffusion on d to the m. I'm on the unit square with I have m particles on in the unit square, and let me describe it before the jumps. Since I'm doing the gathering with probability 1 over lambda, and the process is being run at rate lambda, at a Poisson process of time 1, there are going to be these jumps. But here's the process in between the jumps. It has mean 0, and it has covariance matrix, covariance operator, sigma, I'm going to call it, of z1 up to zm. Those are points in the unit square, which is f tensor product with 2 by 2 matrix, where Fij is equal to, it's equal to P, that's my coin toss probability, times, there's no sigma squared, times pi times delta if I is equal to j, and it's equal to P times the volume of, you take Zi and plus the hand, and you take Zj plus the hand, and take the volume. So look at coordinates I and j, look and see if you put a ball of radius delta around them, if they intersect, take the volume of that intersection, and those are the off diagonal terms. And so if Zi and Zj are separated, then they're uncorrelated, and otherwise so this is a positive definite matrix, and that describes this limiting correlation. Let me just write it down for 2 coordinates, e.g. when m is 2, there's a 4 by 4 covariance matrix, which is A 0 B 0 0 0 B B 0 0 and 0 B 0 A, where this is A and this is B. And what this process is, so marginally, so these are say I have two points in the unit square. Marginally, each is a reflecting Brownian motion, reflecting here, and the x and the y coordinates are independent. But when they get close together, they interact in this way. And I won't describe the gathering. Okay, so backing up. I wanted to try to describe 4 things. One was a class of problems, namely spatial mixing models, and there's just the spatial mixing problems, there are lots of them. The second thing is we have a model that we've been studying that we can prove some things about, and it leads to interesting math problems, and we made some progress studying it. There's more to do. The third thing is this proof technique of shadow permutations, and it's some kind of coupling. The idea, let me just say the one sentence for the idea is in any of these dynamics, once two cards come together into the same pile, they're exchangeable. And once every pair of cards have met, the deck is random. So you have to make that specific. It's not anything like a strong stationary time, but there's this shadow argument. There are lots of models for which it applies, and it leads to nice probability problems. And then there's this limiting diffusion. Thanks for your patience. Thank you.
So I have one first question. So is there a lower bound in terms of m? Because naively one might think that there would be an upper bound that's just a function of delta.
It could well be. That is, in some models. So on the handout I put, Soumik and I started to work with Shorov. There are cases in which it doesn't depend on m. So it's possible, because delta is staying positive. Could let delta go to 0, but I'm not. And so it's possible, no. So no, I don't yet have a lower bound. No. We haven't been working on it. We've just been desperately trying to get any bound, and I said where we are, but there's much more to do, right? So it could very well, and in fact, we do have some situations in which we can prove, not for quite this model, in which a large but finite amount of time is mixing, because it is pretty vigorous, right? And so no.
So there are two different mixing problems here. One is the mixing of the unlabeled particles. You construct the empirical distribution and see how it's close to uniform. Right. And the other is the mixing of permutations of particles. And these two are different mixing problems.
Right.
But the first one, it is quite possible that in constant time, especially, I think it's definitely true coming from fluid dynamics, that in constant time everything is mixed. Yeah. The second one is not obvious. It's the one that we are doing.
It's obvious, but I'm saying, is there a lower bound in terms of m, or is it still possible that even for the second one it will be?
I'm pretty sure we can prove, for example, for one-dimensional where, what depends what the dynamics are, but for example, suppose the dynamics are the hand does nearest neighbor random walk and then cuts a binomial number of cards off and mushes it in with whatever pile it goes to. So then I think we could show it definitely depends on m if you have m sites, because this card will have to move over. The left-hand card will have to move over. You'll have to get there with your random walk, and that'll take a while.
But the random walk, isn't it moving like a distance delta?
My random walk, I was having it. You get to make your own rules. My rules were I'm doing nearest neighbor random walk on n discrete sites, on m discrete sites. But you could.
I'm talking more about the gathering where you gather from a whole delta neighborhood.
Right. I see. No, I see. Here I've let delta, without understanding it, here I've let delta be small. Right. If you were gathering from a positive proportion, then it might be right.
It's a concept. It's changing with
right. Right. So I don't know.
We're getting out of time, so I'm afraid we have to finish. So let's thank Percy again.